Alkynes, cycloalkanes, and aromatics. Alkynes have at least one triple bond between two carbon atoms. And let's just stop for a second. We have alkanes, you have an A there, that has all single bonds. Alkene, with an E, right? Alkene, E-N-E, has at least one double bond. So I'm just going to put one single bond, double bond. And now we get to alkynes, which is Y, and that has at least one triple bond. So they kind of go in alphabetical order there with the suffix. Might help you remember it. The general formula is CnH2n-2, where N is the number of carbon atoms. The simplest alkynes are C2H2, which is ethyne, also known as acetylene, and then C3H4, which is propyne or propylene. And here's the triple bond in each one of them. And here's the ball and stick model showing 3 sticks there for the triple bond, and same here with ethyne. Here's a table of alkynes. We show the first 5 alkynes, ethyne up to hexyne, 1, 2, 3, 4, 5. And you start here with 2 carbons, and then 2n-2, which is our formula. 2 times 2 is 4 minus 2, we get that. So we have C2H2, C3H4. So every time you add a carbon atom, you're adding 2 hydrogens. And here's the general formula right there. Once again, we have a little exercise for you. So please complete this table for the next 4 alkynes and check your answers on the next slide. Well, here we go. For the suffix -ine, right, decyne, nonine, etc., you start with how many carbons, double it, and subtract 2. So let's do the first one. Twice 7 is 14, minus 2 is 12. So that's C7H12. And then hopefully you got the rest of these correct. Carbon atoms can also form ringed structures. And that's what we're showing down here. Each carbon bonds with the 2 adjacent carbons in the ring. In alkanes, those are all single bonds, and each carbon forms 2 additional bonds with hydrogens for a total of 4 bonds. The carbons are located at the vertices with 2 hydrogens attached to each. One example is cyclohexane. 5- and 6-member rings are most stable as their bond angles are very close to the tetrahedral angle, 109.3 degrees. The smaller bond angles from 3- and 4-member rings create a higher potential energy and less stable configurations, also known as higher ring strain. So we're showing here cyclohexane, cyclopentane, and cyclopropane. Cycloalkanes have higher densities, boiling points, and melting points than alkanes due to their geometry that causes stronger London dispersion forces. Usually, the CH2 groups are omitted on the drawings to make them easier to read. You are expected to know that the CH2 groups are present. This is how you most often will see them depicted, just like that, kind of like the old skeletal diagrams we had earlier. This table shows the first 4 cycloalkanes and the general formula for any cycloalkane. Cycloalkanes have 2 fewer hydrogens than alkanes since there are no terminal carbons to which to attach hydrogens, right? Because they're a ring like this, where we had the alkanes in a straight line, you had terminal points here where you could add another hydrogen. So we show cyclopropane through cyclohexane, and the rule is 3 carbons, 2n hydrogens, so it would be CnH2n. So please complete this table for the next 4 cycloalkanes and check your answer on the next slide and use this formula here, CnH2n. So here's our answer. Basically, you just have, for every 1 carbon, you have 2 hydrogens, so hopefully you got all that correct. Benzene has 3 double bonds in a cyclic structure. So here's the structure of benzene, and here's a double, here's a double, here's a double, and on the ball and stick model, it also shows 3 double bonds. It is described as an aromatic compound due to its recognizable aroma. The aromatics are not aliphatic compounds. They are in their own category, so they are not an alkane, alkene, or alkyne. Its ring structure consists of 6 carbons located to the vertices of a hexagon, with hydrogen atoms connected to each carbon. The bonds connecting the carbons alternate between being single or double bonds. Usually, the benzene ring structure is drawn without showing the carbons and hydrogens, and it is assumed that you will know that they are there. Also, it is more accurate to think of the single and double bonds being shared by all the carbons in what is called a resonance structure. So what's the difference between these two? Well, you've got a double bond at this piece here. Here you just have a single bond. The double bonds are all shifted one to the right. Resonance in benzene rings is also shown by just putting a circle within the hexagon, so you don't worry about drawing the individual double bonds. But just to reiterate, you've got this is a double bond, this is a double bond, this is a double bond. The other bonds are single, and on the drawing to the left, the double bonds are just rotated. They're in a different position. And we're assuming that these single and double bonds are shared by all the carbons, which makes it a resonance structure. Toulene is another aromatic compound. It has the same structure as benzene, right here, with one of benzene's hydrogens replaced by a methyl group, CH3. The methyl group is known as a substituent on that specific carbon atom as it replaced a hydrogen atom, or it's substituted for it. Functional groups are specific groups of atoms which have their own properties, and methyl group is a functional group. So, two ways to draw it here, and then with the ball and stick model, that's how it's drawn there. And here's your three double bonds. And here's the CH3 methyl group. One more way of drawing three-dimensional molecules. They use special symbols. So if you see this right here, that's a bond. It's a single bond, and it's a wedge, and it shows that the bond is coming out of the page towards you. The plane lines over here show a bond in the plane of the page. If you have a dashed line, that shows a bond physically going into the page. And finally, if it's a wavy line, that shows it's unknown whether the bonds are into or out of the page, or if your sample contains a mixture of both directions.